Good morning, students. Today we are going to discuss higher order differential equations and its general solution. The first part of general solution, complementary function, and in that also a particular case which is complex and repeated roots of auxiliary equation. In this series, we already covered 3 videos, which was for real and distinct roots, real and repeated roots, and third video was for complex and distinct pair of roots. In this talk, we are focusing on repeated complex pairs of roots. So let us start with this video. As usual, I am considering for reference second order differential equation with form y double dash plus c1y dash plus c2y equal to r of x. Y is depending on variable x, c1, c2 are arbitrary constants, and r of x is random function of x. Now, after defining differential operator capital D as d by dx and d raised to n as d raised to n upon dx raised to n, we can convert any higher order differential equation into its equivalent differential operator form, that is d square y plus c1 dy plus c2y equal to r of x. If I take y outside from the left hand side, it gives us d square plus c1d plus c2 times y equal to r of x. Let us consider this d square plus c1d plus c2 as a function of capital D. So it gives f of d of y equal to r of x. So this differential form f of dy equal to r of x is always our first step in solution. Now let us begin for complementary function, which will be the first part of general solution. And for that I am taking f of d equal to 0. This part f of d which will be equal to 0, and it is known as auxiliary equation or characteristic equation. Once we factorize this and if we identify the roots of this equation, then we may get one of these 4 possibilities. I already covered first, second and third case in the previous videos. Today I am focusing on complex and repeated pair of roots. So let us go through the general process for this type of situation. For instance, if characteristic equation f of d equal to 0 gives m1 m2 as alpha plus or minus I beta and m3 m4 as also alpha plus or minus I beta, that means this equation is with these 2 complex pairs which are repeated. In such cases, the complementary function will take this form. Now we can see the real part of alpha is for exponential function, so it is e raised to alpha x, and beta is for cos and sine in our solution. But now as our roots are repeated, I am considering c1 plus x c2, c3 plus x c4. So remember, if there are complex roots, there will be exponential function as well as trigonometric function. And if your roots are repeated, you need to club the constants. So again you can see clearly for 4 roots, there are 4 arbitrary constants. This is how we should remember a repeated complex roots case. Let us consider some examples. Suppose I take my first example, y raised to 4 plus 2y raised to 2 plus y equal to 0. This superscript 4 in small bracket indicates derivative, and as it is 4 over here, it indicates fourth order derivative. Considering operator form, it gives us d raised to 4 plus 2d square plus 1y equals to 0, and by taking auxiliary equation f of d equal to 0, we can find complementary function. If I take d raised to 4 plus 2d square plus 1 equals to 0, simply gives me d square plus 1 whole square equal to 0, which means 0 plus or minus I is appearing 4 times. So it's m1, m2 as 0 plus or minus I, m3, m4 as 0 plus or minus I. So now, this is the situation where complex roots are repeated. And so, I am taking alpha equals to 0, the exponential function, beta equals to 1 with cos and sine, and I am considering repeated case. So it gives me c1 plus xc2, c3 plus xc4. This is how you should consider repeated complex roots. Let us consider one more example. Suppose we want to find complementary function for y raised to 6 minus 2y raised to 5 plus 3y raised to 4 minus 4y raised to 3 plus 3y raised to 2 minus 2y raised to 1 plus y equals to 0. So this equation is sixth order differential equation. So I am considering operator form and considering auxiliary equation f of d equals to 0. Now you can simplify this very easily by considering this 3d square into two parts, 2d square plus d square. It will give you d square plus 1 whole square into d minus 1 whole square equals to 0. It simply means that here we have 6 roots. Out of the 6 roots, 2 roots are real, which is equal to 1 by this factor, and they are repeated. So m1 equal to m2 equal to 1. And this gives us that there are 4 roots which are complex and they are repeated like this. m3, m4 is 0 plus or minus I, m5, m6 is 0 plus or minus I. So I am writing my first component for real repeated roots, so I am following case number 2. So it is e raised to 1 into x into c1 plus xc2. This is due to the repetition of real root. And for this, I am taking e raised to 0x in bracket c3 plus xc4 cos x plus c5 plus xc6 sin x. So here 1 is beta and 0 is alpha. Alpha is always with exponential, beta is always with cosine sign, and as there is a repetition of the root, we are taking c3 plus xc4, c5 plus x6. Again, there is no such rule that always we have to write down first for real roots. You can take first component for complex roots and you can write down second component for real. That is also valid. The reason is all the c1, c2 up to c6, they are arbitrary constants. Let us take one more example to make this thing clear. That is, suppose I want to find complementary function for y raised to 6 plus 9y raised to 5 plus 24y raised to 4 plus 16y equal to 0. Then we will get differential equation d raised to 6 plus 9d raised to 5 plus 24d raised to 4 plus 16 times y equals to 0. Now, for complementary function, I am taking auxiliary equation f of d equals to 0. It simply gives me d square plus 4 whole square, d square plus 1 equals to 0. Now, if I take my first part as d square plus 4 whole square, then it gives me m1, m2 as 0 plus I, it is y d square plus 1, and m3, m4 0 plus or minus 2y equal to m5, m6. So here my complementary function will take place in this way. So it is e raised to 0x because alpha is 0 over here into c1 cos x plus c2 sin x as beta is equal to 1. Now taking another part for this repeated complex pair. So it is e raised to 0x in bracket cos of 2x sin of 2x, and for repetition of the roots I am taking c3 plus x c4 c5 plus x c6. So this is how you can deal with repeated complex roots. If you have any difficulty, we should again go through this 3 different examples in which I tried to cover each and every possibility of repeated complex roots. In exam, hardly you will find a sixth order differential equation, but to make this thing clear, I am considering sixth order differential equation also. Okay, so I hope all of you understood that how to go for complementary function. At the end of this fourth case, I want to recall that there are total 4 cases, and all these 4 cases are actually with the same procedure. We have to consider differential form first. You have to take auxiliary equation f of d equals to 0 and then factorize it. After factorization, try to classify it into 4 categories: real, repeated, real, non-repeated, complex repeated, complex non-repeated. Accordingly, you should select the value for complementary function. And one more thing, always cross-check your final answer. Whenever you are finding complementary function, remember one thing, that the total number of arbitrary constants, they are always equal to roots of your auxiliary equation, or you can say the order of your differential equation. I hope now it is clear that how to figure out the first part of our general solution, which is known as complementary function. You should again revise all 4 videos to make this thing clear. This part is going to play a vital role in our next section, which will be the second part of our general solution known as PI, particular integral. Thank you.